resistance.
Yeah.
Yes, you just said that. Very good job. Now, remember the equation for resistance was what?
Potential energy of current.
R equals rho L over A. And so in a typical wire, is the L very big? Is the A very big? No. And the P is whatever the P is. And so typically in a wire, we're going to assume that the resistance of a wire is equal to 0 ohms. And so when we're doing our math and our equations, we're going to assume that the wires aren't going to affect the energy of the circuit. In reality, there's going to be a very small effect. In our circuit especially, it's going to be so small that it's not going to matter. If you're doing like a mile-long wire, you're going to be more worried about that than anything else. Remember, these resistivities were like times 10 to the negative 7 ohm times meters. And so it takes, a couple million meters before it's going to become relevant to the actual thing that's doing it. Similar to when we ignored friction at one time. We're just going to ignore that to make our life a little bit easier. The book refers to this as the ideal wire model. It's a very funny, very, complex name for a very different idea. We're going to say wires that show this together. Right, and there's a setting in that program where you can adjust how much resistance the wires have as well. But yeah, if you look at advanced down the right hand side, you can adjust how much resistance the wires actually have. It's set at 0 by default, and then if you wanted to actually include the resistance of the wires, you couldn't put out at the same time. But typically, mathematically, we're going to ignore that. But in real life, wires do very slowly take energy out of the circuit. That's why if you're making a real circuit, you want to use as few wires as possible, or as little wire as possible, so you don't waste energy in your house. But again, on the scale of like a couple meters, it's not going to make a big difference. You're talking about a huge like airplane or something, more wires that ultimately use a lot of extra energy to protect that. So that's the ideal. In your book mentions the ideal wire model. That's what it's talking about. So pretty fancy there. Questions so far? Okay. We're trying to do this little problem your book has. Pretty exciting. Here's a simple circuit in your book. It's got a battery and a resistor in it. So here. There's a very simple circuit. We want to graph out of the circuit the changes in potential as we go around this loop. There's an outdated term that we'll see sometimes called the electromotive force, which is that squiggly E line. Back in the day, when they were doing all this stuff wrong, they used to think that the battery was producing a force that pushed the charges through the wire. That wasn't exactly correct, but we used to call it the electromotive force, and so we'll see this E sometimes. I find it very annoying that it's there. For us, it's the same thing as writing a V or saying the voltage of the battery is 1.5 volts. So I can't erase it from all the pictures in your book, unfortunately. If you ever see an E, it just means the voltage of the battery. So anyway, here we have a battery hooked up to a circuit. It's going to go around the circuit. There's one resistor here, and it comes back around. What you want to do is graph what the potential or the energy of the charge at any given point is throughout the circuit. We're going to pretend that we're a positive charge going around the circuit, even though we know the negative charge the other one can move, but it's easier time to talk about the positive charge. So we're going to draw a graph. We're going to draw that over here and out. We're going to have voltage on one axis, and on here we're going to label each thing in the circuit. As we give the potential energy of gravity, at any point we want to, we can call the voltage in the system 0. And so right here, I'm going to call the potential in the system 0. Call it the 0 energy point in the system. So our graph is going to start right here, and we're going to move around the circuit like that, in a clockwise fashion, as if we were a positive charge. Okay. So as I go across the battery, what do you think that battery does to a positive charge? The positive charge is here. What would the battery be doing here? In terms of the voltage or the potential of the charge, what would it be doing? What would the battery do? Increase energy of the charge. So batteries are charge escalators or charge elevators, and a battery is always going to re-energize a charge. And so in this case, the charge hits the battery at 0 volts, it's going to go up to then 1.5 volts as it goes across the battery. So from the start to the end of the battery, the charge is going to increase its energy 1.5 volts. So that's what the battery is, well, a 1.5 volt battery. Okay? This is not a very complicated thing that we're doing. If you think it's really easy, that's what it is. So if you go across the battery, if you go in the correct direction across the battery, you're going to increase your energy. As I go across this top wire, am I going to be losing or gaining any energy in our ideal wire mount? No, if we're ignoring the resistance of the wire. So what would this graph do as we go across the top wire? Plateau, horizontal line, very good. So our voltage will remain constant as we go across the top wire. This is TW for top wire. So there's no change in potential across that top wire because we're ignoring the resistance of the wire. What happens, do you think, as I go across that resistor to my potential in this circuit? It goes down, and in fact what we'll find as we go forward here, we'll find that whatever voltage goes into a circuit has to, by the time you finish your loop, be the same out at the end. So you could say V start equals V end if you want. Whatever potential you're getting in from a power source will always be used up. The same thing if you climb up a mountain and gain 100 joules of energy and roll down the mountain back to the start, you can never not use up all 100 joules of your energy, right? You can't get 1.5 volts in the charge and only use up 1.3 by the time you're done and have 0.2 left over. And that's not how it works. Whatever energy you start with in the circuit, you have to use up all the way through. This graph is going to come back down to the beginning. That's across the resistor. And that's going to then flatline to the end across the bottom wire because we're ignoring that resistance in the wire. If we didn't ignore the resistance in the wire, then we'd have to bring that graph down to like 0.1 volts and then finish it up to 0.0 at the very end. That's kind of how you work going to this. Yes, sir. Then it would be a short circuit, and you'd be a different kind of thing. So then basically your resistance is 0, and then in your equation, like I equals V over R, you're dividing by 0 then, that's going to mess everything up. So all this math, and to the point of a superconductor, all the math goes out the window once you keep your resistance down to 0. So, good question, but we won't necessarily deal with that. But you can see where that would mess the math up. Questions about that? That was pretty, I don't know. Just the point one making that all the energy is used up in the circuit. All right, last thing for the day, topic we've discussed before, and that is power. And remember what power is? It's measured in watts, very good. What else do we know about power? Force of time, no. So it's going to be the work we do, sure, the work divided by time. What is it in words? And what the words are, not necessarily the equation, or what is it? Good, it's the rate of energy use. And so do you think we use power stuff in circuits? Yeah, heck yeah. And so where in the world of electricity do we often see this word watts?
Light bulb.
Light bulb, good. So a 6-volt light bulb uses up 60 joules of energy per second. Correct? Right, good. 100-volt light bulb uses 100 joules per second. That's why it's brighter. So in the electrical world, we're going to kind of cut to the chase here, because we're running out of time. We know, this is what we know. I'll tell you the power in a circuit always equals the current, or the power of a certain object in the circuit will always equal the current through said object times the voltage it's using. So the current, remember the current is Q over T. That's our equation for current. And so that's kind of where you get your over T part of this equation. Then the V times Q is your work. We also can write this two different ways by substituting in Ohm's law. We can write it as I squared times R, or V squared over R. Power? P? Q, charge per time. This is the equation for current, charge per time, coulombs per second. Those are your three equations for power.